Hi, I am Prashant Kumar PV, Assistant Professor, Department of Computer Science and Engineering, MS Engineering College, Bangalore. In this video, I am going to discuss the last phase of the compiler, that is called code generation. This is the overview. Let us see what is a code generation. Code generation is the last phase of the compiler. It takes as input an intermediate representation of the source program and produce as output an equivalent target program. So this code generation will take the input as an intermediate representation of the source program and it produce the target program in the underlying machine architecture. The requirement of code generator: output code must be correct, output code must be of high quality, code generator should run efficiently. So these are the requirements. The output code generated by the code generator should be mathematically equivalent to the source program. Functionally, target program is equivalent to source program, and the code generator need to produce the target code in the machine language should be of high quality. Code generator should do its work within the time span. It won't take unlimited time, very efficiently produce the target code. While thinking of the code generation phase of the compiler, there are many issues associated with the code generation. So those issues we can list here, issues related to the code generation. One is input to the code generator, target program, instruction selection, register allocation, and finally evaluation order. So one by one we will discuss. First issue is input to the code generator. So we need to define what is the format of the intermediate file, because intermediate file is the input to the code generation. The intermediate representation of the source program produced by the front end may be postfix notation, syntax tree, or tree address code, or similar to that. If you are using postfix notation, it's a linear representation of the source program. Then the code generator should design in such a way that to convert postfix notation into target code. If a graphical representation of the source program we are using, then that is called syntax tree. A syntax tree we are using as an intermediate representation of the source program. Then in such a way the code generation phase need to design, and most probably tree address code will use as an intermediate representation, and that is more similar to the machine instruction, and we have seen different format of the tree address code and its implementation. Code generation phase also use the information which is present in the symbol table, and code generation phase will get the runtime address of the data object from the symbol table. The input is free of all kind of errors. Syntax and semantic errors should be verified during the front end of the compiler, and if any error is there, we can't use the target code. So before moving on to the code generation phase, we should define what is our intermediate representation. So that is an issue related to the code generation. And second issue is target program. So clearly we need to define what is our target program, and target program depends upon the machine architecture where we producing the target program. There are different type of machine architecture like load and store architecture, stack based machines model, and reduced instruction set computers, complex instruction set computers. So the underlying machine model should be clear before starting the code generation, because the code should be run on those machines and which should be suitable to that machine. The output of a code generator is a target program, and moreover that underlying machine architecture, there are different type of target languages we can choose. See, some code generator will produce absolute machine language. So if the target language is an absolute machine language, then and it should execute in a particular memory location, and while writing the absolute machine code, the memory location should be defined. This absolute machine language is suitable for a small program. Then instead of absolute machine language, suitably we can choose relocatable machine language. If we are choosing a relocatable machine language, then there is a need for linker and loader. Usually in relocatable machine language, we can load into any memory location wherever we have the room to load those relocatable code, and subroutines are independently we can load it and we can compile it because they are independent module. So such freedom we will have while we are designing target language as a relocatable machine language. We are writing target programmers in assembly, then there is a need for assembler. Then the assembler will convert target language into either absolute machine language or locatable machine language with the help of linker and loader. If the output of an assembler is locatable, we can link and load. That means if target language is an assembly language, we need to think of assembler, linker, loader, etc. Those modules also required for the running of the source program. And writing language in assembly is much easier compared to other cases. So before starting code generation, we need to decide which is our target program language. There is another issue. Third one is instruction selection. This instruction selection depends on 3 points. The difficulty of instruction selection depends on the level of intermediate representation and the nature of instruction set the target machine support. And third one is the desired quality of the generated code. First one is the intermediate representation is the input to code generation. There are different level of intermediate representation. They are high level intermediate representation, medium level intermediate representation, and low level intermediate representation. And what is in high level intermediate representation is which is little more independent of the underlying machine. Machine dependency in high level representation is comparatively less compared to low level IR representation. So what is the level of IR? If it is high level, then the selection of instruction for writing the target program is little bit difficult. But if the IR is in low level, then selection of instruction while writing target program is little bit easier, because IR is low level IR is more related to the machine instructions compared to high level IR. Second property is the nature of instruction set the target machine support. Like suppose we want to perform some floating point operation and the underlying target machine is not supporting floating point operation, then certainly there is a gap. So we need to find other mechanism to fill that gap. Such incompleteness is there in the instruction set, then we need to take care of by selecting the instruction and performing the operation. Similarly, sometimes some target machine will support only a particular type of data. It may not support all type of data. Then uniformity problem will come. Then if uniformity is there, then handling such a non-uniform data or non-uniform functions, it is little bit difficult. Writing the target code for such a target machine is difficult. Then instruction speed and machine idioms. This is like suppose we want to perform increment a variable by 1. So we can perform in two ways. Either we can use INC if the instruction set support INC, or we can add the variable with the 1. Both the instruction will do the same function, but the instruction speed to doing the operation and the machine idioms are different. So depends upon the instruction set, we need to choose the apt machine idioms and machine instructions to do the functions required for converting. So then only we will get enough speed. Similarly, size of the instruction set. If the instruction set supported with the machine is very large, then choosing an instruction is a time-consuming process, which is suitable to do the operation is time-consuming process. So size is also a factor of writing target program. So that's why nature of the instruction set supported by the target machine. Then the third point while selecting the instructions is desired quality of the generated code. If speed is a factor and optimization is a factor, that means time and memory utilization is a factor, then we need to work on more about the instruction selection. Then only we will get a quality code. That's also a factor. Then next issue, register allocation. And we know that registers are a small memory which will hold information and which is very near to the processing unit, we can use that register as an operand for performing some operations. Register is a short and faster than memory operands. The register usage is divided into two subproblems. So because of this feature, so the usage of register is divided into two problems. One is register allocation, second one is register assignment. And what is a register allocation? Register allocation is during which we select a set of variables that will reside in the registers at each point in the program. So register allocation is nothing but we are deciding at a point of time what all variables we need to keep in register. So in register allocation, we are finding a set of variables which should reside in registers. So that is related to the selection of variables. And register assignment is during which we pick the specific register that a variable will reside in. And second, assignment is nothing but okay, already we have selected set of variables which we should reside in the register, and we are selecting the register at a point of time in order to storing the picked variable. So second problem is related to the selection of registers. First problem, register allocation, is related to the selection of variables which we store in register, and these two are very hard problem, and finding an optimal assignment of register to the variable is an NP complete problem. And we treat this register allocation problem as a graph problem, and by using graph coloring problem to solve some extent this register allocation problem. So effectively selecting the register for storing the variable will speed up the execution of the program. So that is also an issue in code generation. Last issue is choice of evaluation order. The order in which the computations are performed can affect the efficiency of the target code, and some computation order require fewer registers to hold intermediate result than the other. That is the point. See which order we are choosing to run the executable code. Some order require fewer number of registers compared to some other order. If we require fewer number of registers, then we can hold more variable into the registers. If you are using effectively the register for computing the instruction, then automatically speed will increase. So that is, the evaluation order will indirectly increase the speed of execution. This is also a very difficult problem. Picking the best order of evaluation is another NP completes problem. So there is no algorithm exist in polynomial time identifying the best order of evaluation of the given program, but choosing the appropriate order will speed up the execution. So these are the main issues related to code generation. And while designing a code generator, we can list the issues related to code generator design. One is understanding the machine architecture. That is very important because run the target code on that machine model. Then operation code support by target machine instructions, because with the help of this operation code, available operation code, we need to perform the task which is written in the high level language. The instruction support is there, then directly we can use. If instruction support is not there with respect to target machine, then we need to do it indirectly. Then doing indirectly will again create lot of problems. Then the support of the addressing modes of the instruction set of the target machine. Then what is the cost of the instruction? Cost of the instruction is nothing but how much memory cycle it will use, how much while running that instruction, how much CPU cycle it will use, because these are the two scarce resources, and while executing one instruction, what is the memory cycle and what is the CPU cycle required. That is the cost. Next topic is a simple target machine model, and we will study this simple machine model, and we will produce few target machine in assembly. We will not study absolute machine code or relocatable machine code, because those are very difficult to understand. So that's why we will produce target machine in assembly language. Those topics we'll discuss in the another video. Thank you for watching this